All right, good morning everyone, and welcome to Chabot Science Center's live science show virtually. Woo! We are super excited to be back with you all here today. Thank you to those of you who are returning from our first week. We are going to continue our journey of learning a little bit more about light, and we're going to be playing with light and exploring a little bit more about why light is important in our lives. So, we are going to do a demonstration for you today, and what live science is showing off a cool phenomena, which is like something that happens in science that might be challenging to explain or to understand, and we're going to try to break it down together to figure out what's going on. So I'm going to need your help in the audience, as all of my fellow scientists out there. I'm going to need your help to make observations of what you're seeing today. So things that you notice, things that you may think are curious or interesting. And I'm also going to need your help to make predictions of what you think is going to happen next. And I'm going to need your help to make explanations of what you're seeing. So kind of trying to put the pieces together to figure out why we're seeing an interesting phenomena or an interesting happening that we're seeing. So hopefully you're ready, and if you want to warm up your chat fingers, you can do that and type hello into the chat. We are streaming to you live from Chabot Space and Science Center on YouTube and Facebook. And just a reminder, if you are joining with your class or if you're joining us as part of virtual learning, let's remember to treat this virtual room like your virtual classroom. So we want to make sure that we are treating each other with respect and being nice and using kind words with one another. That's kind of our Chabot way. Hi, hello. And we want to just make sure that we are working together and doing science as a team and as a group. So thank you all in advance for being amazing scientists. Woo! During this time, Chabot Space and Science Center is not open to the public, but we are providing free virtual programming like this. So if you're an adult logged on right now and you would like to help support us in providing virtual programming like this for free to students, teachers, and community members, feel free to click the donate button or head to our website at chabotspace.org and click donate once you get there. That helps us provide these programs, and we appreciate the donations in advance. Thanks. All right, friends. So today we're going to do our demonstration, and we're going to be talking about light. Luckily, all of the things that I'm using today we can find at home and are safe for me to use. We typically start our live science shows off with a safety check to make sure that I'm going to be safe, but today we don't really need to do that because everything I'm going to be working with is pretty safe. So the only thing that I'm missing, I think, is probably going to be my trusty lab coat. And that's just because I like it. So we're going to get my lab coat on. Nice and clean. Gotta love that white coat. And now we're going to get into our demonstration about light. And today we're going to be talking about light and color specifically. So we're going to be talking about why color is a thing and how light and color can work together. Unfortunately, I don't need my safety goggles today. I could put them on for fun, but I think I left them in a room. All right, friends, so like I said, I'm going to need your help to make observations. And what we're going to do today is we're going to be working with these interesting objects in front of me. Does anyone recognize what these objects are? And do you notice anything about them that is different from what you might usually see on an object like this? If you know what it is, go ahead and type it into the chat and put any observations that you might have of what these objects are in front of me. Yep, these are light bulbs. Yay! Which are important in creating light, but they're a little bit different you may have noticed that these light bulbs have some colors on them. So we have a green, we have a blue, and we have a red. No, these are not cups sitting with white balls. They do kind of look like ping pong balls though. Good observation. But these are light bulbs, so we're going to be using them and turning them on and off, and we're going to be using these colored lights to play with color a little bit. Okay, so what's going to happen is I'm going to show you a shape. Now this shape is going to have a color, and what I'm going to need your help to do is to guess what color that shape actually is. Except we're only going to look at it with one light bulb color at a time. So it might be challenging, but I want you to just make a guess of what color you think this shape is. And before we do that, I have to kind of tilt my laptop up a little bit so the light bulbs don't shine in your eyes. And I'm going to ask my assistant to turn the lights off. It's gonna get a little dark. Ooh, spooky. Okay. So, like I said, we're gonna need your help to make a guess of what color you think our shape is. So the first color light we're gonna look at is with our red light, and I'm going to hold up our circle. Now take a look at this circle. It's on a white piece of paper, and go ahead and type into the chat what color you think this circle is. And I'm going to wait. We've got a little bit of a lag, so I'm going to wait for my assistant to read off some of your guesses of what color you think this is. What color it looks like to you. Blue. Good guess. Got a guess of blue. I know the red light is kind of intense. It looks a little spooky, but don't worry. Red, blue. All right, now we're gonna turn on just our blue light, and we're going to see if it looks the same color to you. So now, with our blue light on, does this circle look the same color to you? If it looks a different color, you can guess that color in the chat. Blue, white, yellow, blue, blue, red, yellow, blue, red. Oh my gosh, lots of guesses. And then we're gonna do the same thing. So we're gonna turn on just our green light. Go ahead and make a guess. What color does this circle now look like to you? Does it look the same as it did before, or does it look different? It looks the same. Some people are saying it looked kind of yellow, and oh, now maybe it's purple. Interesting, blue mirror. So we've got a lot of different guesses coming in on our chat. A lot of blues and some blacks, maybe some yellow, maybe purple. So what we're gonna do now is I'm gonna turn on all three lights together, and we're gonna see if that makes a difference. So we're gonna take our green light, we're gonna turn our blue light on, and then we're gonna turn our red light on, and we're gonna take a look at this circle, and I'm gonna ask Olivia, my assistant, to turn the lights on in the room. And what color do we see our circle is? It's blue. So those of you that guessed blue, you were right. But if you guessed a different color, that's okay, because there's an interesting phenomena happening when we look at this blue circle with just red or just green light. So what we're gonna do now is we're going to repeat this with a different color shape and our lights again. And I'm gonna go a little bit faster this time, since we've already done it once, we kind of know the drill. So I'll hold up the shape, we'll look at it under red light, blue light, and green light, and you can type into the chat what color you think it looks, and think about whether you think it looks the same color the whole time, or if it looks like it's changing. All right, so we're gonna turn the lights off, and I'll turn all of my lights off. Now, we're going to go into the next shape. So now we are looking at this square shape right here. It's probably a rectangle. I cut it myself. It's not perfect. And remember, it's okay if your guess is wrong. It's not a big deal. We're kind of just figuring this out together. And I want you to also think about not worrying too much about right or wrong, but thinking about why these shapes are looking different in each of these lights. All right, so this is our first shape, or our first light, our second color shape. So what color do you think this shape is? Now it's in our red light. All right, we've got some guesses of red. Now we're gonna turn on our blue light and we can take a look at the shape. What color does this shape look like to you now? Does it look the same as before? Does it look different? We've got red, orange. All right, now we're going to try it in our green light and we're gonna see red or orange, good guesses. In our green light, what color does this shape look like to you now? Does it look the same as it looked in the blue light or in the red light? It's the same shape, I promise. It may look like it's changing, but that all has to do with the light. Orange, purple. All right, let's see by turning on all three of our lights together first, if you can tell what color shape this is, and then we'll turn on the room lights. It's red! Woo, woo, woo. If you guessed red, you were right, but if you didn't guess red, that's okay, because once again, this is an interesting phenomena, and when we have certain lights on, this red shape looks very different colors. So even if you guessed purple or if you guessed blue, red is kind of a combination of purple or blue, which has something to do with color, but also it's close to orange. It's close to pink, so you've got a lot of good guesses going on here. All right, we're gonna repeat this one more time with one more shape, and then we're going to explain why these shapes seem to be changing colors in each of these different light bulbs. Are you ready? All right, last one. So we're gonna turn our lights off. And we're going to start with our third and final shape. Ready, go. All right, so our last shape is this little triangle shape. And in our red light, go ahead, take an observation real quick, take a look-see with those eyes. Let me know, what color does this triangle look to you in our red light? I think it looks kind of like a black color, kind of like a dark brown. It's not very colorful to me. Alrighty, let's see. Yep, I agree. It definitely looks kind of black. Alrighty, now I'm going to turn off our red light and we're gonna look at it under our blue light. Doo-doo-doo-doo. What do you think now? Does this triangle still look black to you, or does it look different? What color does it look to you now? And then we're going to switch one more time to the green light and go ahead and take a look at our triangle now and let me know what color you think this triangle looks to you under our green light. So it may have looked black under the red light. It looked kind of blue under the blue light, and under the green light, maybe it looks a little green. It looks kind of white to some of us. Maybe it still looks black. It looks devoid of color altogether. All right, so let's turn all three lights on, and if we can tell based on all three lights, what color is our triangle? It's green! Yeah, it's kind of like a Kelly green. Good call. That's very specific on the green. And we could turn the room light on too to kind of see it even better. So this is a green triangle. So if you guessed green, awesome job. If you didn't, that's okay. So we had three different shapes of three different colors. We had a red square, a blue circle, and a green triangle. However, Olivia, can you turn the lights off? We're gonna turn the lights off again. However, when we look at these three shapes, under just one color of light, like our red light, they may not appear the same as they do under our room lights, under our white light. So I need your help to figure out what is going on here. I would love to hear from you. Why do you think when we use just one light at a time, our colors appear different? They appear kind of dark, maybe black. It's difficult to tell what color these objects are in just one light. But when we turn all lights on together, then they look the normal color that we're used to seeing. So under just green light, just blue light, or just red light, these colors seem off. But when we turn all three on, we can tell that they're red, green, and blue. So I'd like to hear from you, from my fellow scientists out there. Why do you think we can see the colors better with all three lights on, but we cannot see the colors very well with just one light on at a time? I'll give you about a minute to type into the chat your guess of the science of why we can see color better when we have all three lights on and we can't see color very well with just one light on. So go ahead and think of a reason, think of the science, and then I will help get into the explanations behind our colors and our light. And we'll check both our YouTube and our Facebook chats. Any reason why you think colors are so easy to see with all three lights on? Okay, so colors mixed makes different colors. Because red, blue, and green makes white, yes. It looks like an illusion. You're right, this is kind of like a visual illusion. It's almost like we're playing tricks on our eyes. You don't know, and that's okay. Sometimes it's kind of difficult to figure this out. Light is pretty challenging to understand. Yeah, reflecting light can bounce off the pictures. Mixed makes white, and it's an illusion. All right, so those are really good guesses, and a lot of you are pretty much on the spot. Olivia, could you turn the lights on? So what we were dealing with today was an illusion that we can create using light. Now, light is energy, and light is all around us all the time. If I turn the lights on in this room, there's light traveling from those lights outward, and it's bouncing all around the room, all around me. But light, because it has energy, it's actually traveling in invisible wavelengths, which are squiggly little lines that the energized particles of light move along until they bounce off of something, and then they move backwards in a different way. So, wavelength of light can actually determine what that light looks like. Not all light looks the same. It doesn't all look white. Sometimes it looks green. Sometimes it looks blue. And the different colors of light that we see are actually light that's traveling in a different type of wavelength. So the movement of light can determine how it looks to us and our eyes. That's how we get colored light, because different energy of light makes different colors. So light is all around us, and it travels in wavelengths. But when we're looking around in like a room like this, and we're talking about light that comes from something like a flashlight or the sun, we call that white light. So if you're at home, you can go ahead and say, white light. Now, white light looks white to us, but what it actually is it's all colors of light combined together. So white light may look one way, but if you were to split white light up using something like a prism, that white light actually has red, orange, yellow, green, indigo, blue, and violet light hidden inside of it. But you can separate that white light out into its all different wavelengths of color light using something like a prism. We also see this if you've ever seen a rainbow up in the sky. How many of you have seen a rainbow before? Pretty awesome, maybe on like a rainy day. What you're seeing is white light from the sun traveling through the clouds. And the clouds have little droplets of water that act like a prism. And what that does is it filters out that white light to show the rainbow light that's hidden inside of the white light. So, white light has all colors of light hidden inside of it, which is extremely important for seeing color, because white light allows us to get color in the objects around us. Now, how do you think that works? How do you think shining white light on an object helps the object suddenly have color? Well, we're going to break it down. When you shine white light on an object, say you were to shine it on these tongue depressors, popsicle sticks, always forget what these are. The white light is shining onto these and it's bouncing off of them. And as the white light shines onto these, some of the wavelengths of this light are absorbed. That means that the wavelength is absorbed into the object. And some of the wavelengths of light are reflected. That means they bounce off and away. So if we were to look at something like a pumpkin, for example, because it is October, white light that's shining on the pumpkin is coming in, and it has all of those colors of wavelength of light hidden inside of it. So we can't see the rainbow, but we can imagine that all the colors are bouncing towards the pumpkin. But because the pumpkin looks orange, that means it's absorbing the violet, the blue, the indigo, the green, the yellow, and the red light, and what's reflected off of it is just the orange light. So when you look at something that's colored, the reason it looks colored is because it's actually reflecting that wavelength of light. So that's why we see color. But if the light that we're shining on an object isn't white light, that limits what light is available to bounce off of the object. So for example, if we were to take our popsicle sticks, in white light you can see all of the different colors of popsicle sticks that I have in my hand. But if we turn the lights off, Olivia, can we turn the lights off? And I turn on just a blue light, we no longer have white light hitting the popsicle sticks. We only have blue light, which means there's only blue light available to reflect off of these. Any objects that are not blue, so objects that are red or green or yellow, they're not able, what they do is they absorb the blue light, reflecting no light at all, so they might look black, or reflecting all the blue light, looking more of just a blue color. The same things happen if we look at a red light. Even though we know these popsicle sticks are all different colors, when we only provide it with red light, there's only red light available to reflect off of these sticks. That means objects that are red, such as the popsicle sticks that are red, orange, or yellow, they reflect the light looking very bright, like a white color. But objects that are blue or green or purple absorb all of that red light, reflecting no light at all, which makes them appear black. The same thing happens when we use a green light. Any objects that are green or greenish reflect the green light away, boop, and any objects that are blue or red absorb the green wavelengths of light, reflecting no light behind. That's why they appear black. That's the same thing that we were seeing when we looked at our three shapes. Because we weren't giving our shapes white light, we were not giving our shapes all of the colors of the visible spectrum of light to reflect off. That means that some of these colors are not able to reflect the true color that they are. But once we give them all three, we are combining all of those colors of light to make white light. Because as we said earlier, white light is a combination of all colors of light. So in a way, our demonstration today showed us that when you combine all colors of light, you can reverse this and take rainbows and turn them into white light. But if you take white light and break it apart into just red light, just green light, or just blue light, that limits how well you can see colors, because white light is one of the biggest reasons why we can see colors in the world around us. Hopefully, y'all could understand that and follow along. If you have any questions, you can feel free to type them into the chat right now. But understanding light and the world around us is very tricky because we can't see light. So it's okay if you still feel a little confused or a little lost, but understanding light will be a long journey that even I, as an adult, am still figuring out exactly how light works. If you want to try something like this at home, you can take something like colored cellophane, which is clear plastic that has a color to it, and you can try to look at things around you through a colored filter. And you can notice how the world is changing around you based on the filter that you're looking at the world through. That's one way that you can kind of take this experiment and do it at home. All right, we have a question. Do primary versus secondary colors make a difference, green, 6 versus red/blue? Do primary colors versus secondary colors make a difference? Technically, if I were to have like a magenta and a cyan and a yellow light, then I would have the ultimate white light, so it would make a little bit of a difference. Right now, I'm just working with the basic primary colors, so I'm getting an effect of general white light. We can see most colors right now. But yes, if I were to use just secondary colors, it would look very different in the fact that it would just be more colors available, if that makes sense. So right now I'm just working with the absolute basics, which is red, blue, and green. And I had a diagram, but I think I left it at home showing how I combine. Here we go. So this is a picture I was going to show earlier that kind of shows, we can turn the room light on. So this is called additive mixing. When you're working with light, if you combine red, green, and blue all together, you can create white. But if you combine just red and green, you can actually get colors like yellow, just green and blue, you can get cyan, and just blue and red, you can get magenta. So the primary colors can make all colors, but if you were to have these colors also, the secondary, then you would have the ultimate white light. If that makes sense, hopefully. Do red or blue stars also shine white light? That's a really good question. When you look up at the sky and you look at a star, it might look colored, and what's happening is it's actually burning a specific type of gas. And those gases, when they burn, have a specific energy that makes a different color. So technically, I do not think they're giving off white light because they are solely giving off the color of the gas that they're burning. But some stars are more of like a white light star. Is this what you see when you wear sunglasses? Like the different colors? Is this what you're asking? When you are looking through sunglasses, what those are doing is they're actually filtering out some light. So white light that's around us coming from the sun is the visible light that we can see, but there's also light that isn't visible to our eyes. So when you wear a pair of sunglasses, you're actually filtering out light like UV light, which is different wavelengths besides color light. They're, I think, higher energy? I'll have to check. But it's different wavelengths of light that don't fall into a visible spectrum, so we cannot actually see them. So what that means is we need to protect ourselves from them because they can be damaging to the eyes. So sunglasses help filter out UV light, not just colored light. But some sunglasses do have a filter on them that has a specific color, like mine, for example, are kind of a blue tint, so that can affect the color that you're seeing as well. Good question, and good relation to real life.
If white light equals rainbows, then why do only prisms show it?
If light what?
If white light is a full spectrum of color, why do we see it only if a prism breaks it up?
That's a good question. Someone just asked, if white light is a rainbow of colors, why do we only see it when a prism breaks it up? I actually don't know the answer to that. I tried to look this up yesterday and I just got a little too confused. But it has something to do with this additive mixing. I'm not sure exactly on the physics behind why when you add the colors together of light, it makes white light and it doesn't just appear like rainbow all the time. But that's a very good question, and I encourage you to try to look that up and find an answer, because I myself thought about this and was very confused, and then I think I got distracted, to be honest. So look that up. That's a great question. And if you have a prism at home or something like a prism, you can actually look at how it breaks the light up into its different wavelengths. But you stumped me on that one. It always happens at least once. Any other questions that we've got from our audience? These are good ones, by the way. All right, while I'm waiting for any last-minute questions, I just want to let you know that if you enjoyed our live science show today, we do have a live broadcast every week, Wednesday at 10:30 to around 11 a.m. And it's pretty much this. This month we're exploring light, so next week we're going to do another demonstration about light. So feel free to tune back in and we will learn even more. We also have other free virtual events that are happening through Chabot Space and Science Center. If you want to join with your friends, your family, or your adults around your house, you can join us. We have virtual telescope viewings where you can look through a telescope and do some stargazing. Those are on Saturday evenings, usually around 9 p.m. And we also have a talk next week on Tuesday at 7 p.m. with a scientist from SETI, which stands for Search for Extraterrestrial Intelligence. Those are the people that look for aliens. So if you want to hear a talk from someone who's trying to find aliens in space, you can tune in with us next Tuesday, I think it's the 13th, at 7 p.m. Did we have any questions?
Can water hit the light to see a rainbow?
What was that? Is water?
Can water hit the light to see a rainbow?
Yes, yeah. So water, someone asked, can water be used like a prism to see a rainbow? And the answer is yes. But specific, it usually works when it's up in the sky, so all of the water droplets are kind of refracting and dispersing the light at its different wavelengths, and so you get that rainbow. But if you have it on like a window or something, sometimes it can even create like a mini rainbow through a window. But water is a little tricky. It has to be kind of in the specific format, phase, state, to actually create that effect. That's why we don't see rainbows all the time. It only happens sometimes because it's a special phenomena. Yeah, those of you that are logging off, I hope you all have a great day too. Thank you. So the Chabot family helped me answer our question of why, when we combine colors, we get white light. It's all based on the light receptors in our eyes. So it's actually biology, it's not physics. So thank you so much for kind of helping me correct that. Because light is kind of like physics, but our perception of light is kind of like biology. So we have cones and rods in our eyes. Cones help detect color, and when they see the full spectrum of color, the cones interpreted as white. Super interesting. Thank you. I love having scientists on the line with me. All right, friends. So I just want to say thank you all for joining us today. And if you liked what you saw, tune in next week, Wednesday at 10:30, and tune into our other free events that are happening this upcoming week. While the center is closed, if you would like to help support us by making a donation to Chabot Space and Science Center, feel free to click the donate button or head to our website, chabotspace.org, and click donate there. Thank you so much to those of you that can donate in advance and help support. If you're interested in becoming a member, you can also do that and support us in that way. And we also have a collaboration t-shirt with Chabot, with Chabot Space and Science Center and Oaklandish, which is a company based in Oakland that helps support local stores, brands, and whatnot. And they're selling this super cool shirt that actually glows in the dark, and some of the proceeds helps go back to Chabot and help support us. So those are some ways you can help support us, or you can keep tuning in live. And if you are a teacher with your classroom, feel free to check out our website because we do have some virtual field trip offerings coming soon. So check out our website for more information on that. And we hope you all have a good day. We hope you stay safe, get registered to vote, and we'll see you all next week. All right, stay safe, stay curious. Thank you all so much.